When it comes to cosmic exploration, highly sophisticated problems are discussed. How do humans hibernate? What to eat in space? Have you ever wondered what travelers traveling in light speed in dark sea of stars can do if they get lost? And don't forget they're traveling through three-dimensional route, which is even more difficult. This time, let's explore how to avoid getting lost in the universe. Star observation is a solution given by scientists. The development of science and technology allows us to use radio telescopes to observe a mysterious star. It's called pulsar, and we can think of it as a neutron star that rotates. But there are many span neutron stars. Why is it the only one that is a pulsar? It's actually determined by the rotation obliquity of the neutron star. When a fixed star turns into a neutron star, it rotates faster, reaching a maximum about 700 revolutions per second. At the same time, radiation beams are ejected from the ends of its magnetic poles and rotate along with it. A neutron star can be discovered and honored as a pulsar only when it rotates at an angle that is just right for the radiation beam to cover the Earth. Since its rotation is difficult to be changed by external disturbance, pulsars have a stable rotational period like a lighthouse and sea. Its excellent temporal stability has society the scientists as a natural locator beacon in the universe is just around the corner. How does it work? There are many pulsars scattered throughout the galaxy. Traveling through the universe, whenever the spacecraft approaches a pulsar, its impulse signal reaches us earlier, and vice versa. Based on the time difference, we can calculate the position of spacecraft to each pulsar. To achieve overall location and navigation and determine correct flight path, reference locations should be put in consideration, such as solar mass center. We establish a space rectangular coordinate system with solar mass center as the origin. The graph shows the geometric relations of spacecraft, pulsar, Earth mass center, and Sun mass center. We can calculate the time difference between arrival same impulse signals and solar mass center and the spacecraft, and solve for the unknown by detecting for pulsars simultaneously. According to the way we can derive the relevant unknown to achieve the independent navigation of the spacecraft in 3D, but only if we find pulsar first. This is one of the major problems in the field of astronomy. But the pulsars suggest strong signals that they become particularly weak by the time they reach the Earth. Normal radio telescope vision cannot find them. Only a large aperture telescope can make it. A large aperture bit, 500 meters. It's located in mountains of Guizhou Province, China, and is the world's largest single aperture radio telescope currently, aka the Chinese Sky Eye. Theoretically, FAST can see objects 13.7 billion light years away from it. FAST can collect about 500 terabytes of data a day and 30 million signal pictures in a week. What do you think those pictures look like? Like this or this? Actually, this is what they look like. The stars are so far away from us that we need to calculate and analyze them to find latent pulsars. Such a huge amount of data would take a year to process through with previous technology. But a new technology introduced by National Astronomical Observatory for 3 days, which is Testing Cloud plus AI. AI refers to computer vision technology of Testing YouTube Lab. The signal processing is divided in two main stages: pre-processing and image recognition. Influenced by the interstellar medium in the galaxy, the impulse signals received from the pulsar are laced with many impurities. Pre-processing is to eliminate these impurities from the signal map. It includes removal of RFI, D dispersion, and FFT. Let's take D dispersion as an example. This is a chain chart of the growth power of Vela pulsar over time. D dispersion can bring back their original appearance. Different pulses passing through different interstellar mediums produce different dispersion effects. To accurately eliminate these dispersions takes a lot of computing power. That's where Testing Cloud forms. Compared with ordinary computers, it has a daily quantity of computation of hundreds of petabytes. At the same time, it optimizes the algorithm to allow the GPU to participate. After pre-processing, we enter the identification and screening phase. Guess which one is the pulsar? This is interference. These two look very different, but actually they're pulsars. To be able to read it, we'd have to be at least a PhD. While AI is a faster learner, xM's has specially designed an AI solution based on multi-model plus semi-supervised learning. Together with Tesla-class computing power, it can pre-screen images with pulsar features from massive signal maps quickly. Its faster report rate is 98% lower than traditional AI model. The combination of Tesla Cloud and AI increases the overall processing speed to 120 times that of the traditional model. In addition, AI can assist in the search for astronomical phenomena with more specific radiation mode and more complex celestial motion, such as single pulses. Compared to regular periodic pulses, single pulses are susceptible to intermittency and irregularity. U2 AI's parallel search by periodicity analysis plus dynamic analysis makes single pulsars less easy to hide. So for testing U2 AI astronomical exploration program have searched for more than 22 pulsar candidates from the sky observations. Testing U2 has also started AI processing radio signal of M31 Andromeda Galaxy. The AI also contributes to detection of other astronomical phenomena such as faster radio bursts and binary star systems. The National Astronomical Observatories of China's and Tesla's plan of seeking stars has proved China's technology strength in cosmic exploration. These distant cosmic lighthouses will always guide us to travel the universe without getting lost. Thank you for watching. Please hit the like and subscribe button if you enjoy it.